Hi, this is Daniel Wong from Mr. Hap's Period 1 Calc BC class, and today I'm going to be talking about how you can use your TI-Nspire, specifically for Calc BC on the AP exam. So let's jump straight into graphing. Graphing is something that is pretty important, especially in Calc BC, so you can know what kind of graph you're dealing with, especially if it's not immediately obvious. So there's four major types of graphs. One of them is pretty simple. It's going to be when you have y equals something. So these are going to be your lines, your parabolas, whatever. And you'll see that it says f1 of x, and this just means that it's a function that's defined in terms of x. So you can just treat that as like a y or y1. So let's try graphing something. If we want to graph this, it's going to give us the graph. And if we wanted to um, zoom out, we could go to Windows Zoom, click out, click on where you want to zoom from, and it will zoom out for you. And now let's suppose that we wanted to only look at values of the graph where x is bigger than 0, so only the positive. Well, we can use this vertical bar, which is found on the control equal sign menu, and this vertical bar means such that. So if we wanted to graph x squared minus 6 such that x is greater than 0, we would just type in x is greater than 0, and all of a sudden it's going to only show us values when x is greater than 0. This is pretty useful if you want to only look at values of your graph between certain points. Our next type of graph is going to be our graphs where it's still in Cartesian coordinates, but it's not very manageable to solve for y. And these are going to be your your hyperbolas and your ellipses and even your circles. So how are we going to graph these? Well, if we go to menu, graph entry, and equation, all of these things are going to be here for us. So that way we don't have to solve for y ourselves. So if we wanted to graph a hyperbola that's left and right, we would go here. And if we wanted to graph the most general conic section, it would be under this general. And you can just input all of your constraints and your values into this input box. Next are going to be your polar graphs. You might recall these are when it's r in terms of theta. So if we want to graph these, we go to graph entry and polar. So suppose we wanted to graph a spiral. We know that's r equals theta. So if we wanted to find theta, we have to go to this pi button, and this pi button is going to contain all of our most common symbols like pi and I. So we find theta there, we press enter, we graph it, and notice that this graph only goes around once. Let's say we wanted it to go around twice. Well, we would change these bounds. So notice here it has 0 smaller than pi, smaller than 2 pi. So if we wanted to make it bigger, if we wanted it to go around twice, we would make it from 0 to 4 pi. And notice that we can't actually see our whole graph. So a way that we could see our whole graph is to zoom out, but I think a better way is to use this Windows Zoom fit function, or thing, fit. And if you click fit, it's going to automatically open up or zoom out or zoom in and give you a perfect picture of your graph that's fitting nicely into your screen. So that's polar. And one special case of polar that I want to talk about is when you have something where it's r squared equals some function in terms of theta. So these are going to be your lemniscates, which look like sideways 8s. And you can't actually edit anything on the left side of this equal sign. So you can't type in r1 of theta squared equals cosine of 2 theta. What you have to do is you have to make sure it's r1 of theta equals something. So in that case, you would have to do r equals the square root of cosine 2 theta. You can't have r squared equals cosine of 2 theta. So if we do this, we see that we get our lemniscate, but notice that it's super tiny. So if we wanted to get a perfect zoom, we would go to Windows Zoom and then go to Fit, and then we'll see our lemniscate. So our last type of function is going to be our parametrics, and these are when x and y are both both defined in terms of some third variable t. So how can we input a parametric? Well, we go to menu, graph entry, parametric. We'll see that we can input our x and our y in terms of t. So we could have like x equals t, y equals t minus 6, graph that. And notice that it's still only going to be from 0 to around 2 pi. So if we wanted to make it longer, we could just change these bounds, and um, then we would be able to make our line longer. So that's graphing. Now we're going to move on to the other half of our calculator, which is our scratch pad, and this is when you're computing or differentiating or integrating, and those are the two things I'm going to be focusing on. So something to note is that the TI-Nspire is going to be a computer algebra system, which means it evaluates everything symbolically, which means that you don't necessarily have to put in the bounds for your integral and have it integrate something numerically, because it will be able to find an antiderivative for you. So suppose we wanted to integrate some function x cubed. We don't have to give our calculator bounds. We can just input that in, and the calculator will tell us its antiderivative. So that's pretty cool. Taking a derivative is just as simple. You click on this d by d something operator, and you indicate the variable you want it to be differentiated with respect to, and then we can immediately see that the calculator can find the derivative symbolically. Suppose we want to do things numerically. Well, for an integration, we are going to use this function, which has the upper and lower bounds. So if we wanted to integrate from 0 to 9 of x cubed with respect to x, our calculator can also do that for us. And note that this will give us a fraction in lowest terms. If we wanted to get this as a decimal, we would press Control equals. And notice that above this enter, there's going to be those curly equal signs, which mean that it's going to round. So that's how we can get a decimal approximation. And finding a derivative at a certain point is less obvious, but if we wanted to find the derivative of x cubed at x equals 5, one way to do that would be to take the derivative and then plug in 5 into the derivative, which would give us 3 times 5 squared equals 75. But a better way to do this is to actually use that vertical bar. That means with respect to. That means such that. And we looked at that earlier, and what this means is that we're going to be finding d by dx of x cubed such that, and we can type in x equals 5, and it will evaluate the integral such that x equals 5 and return 75 to us, which is what we want. And one last thing I want to cover is implicit differentiation. You can't actually use this d by dx function to find an implicit derivative. Your calculator actually has a built-in function called impdiff, and you'll notice that it's a built-in function of your calculator because it turns from italic text to normal text. So suppose we had some circle with radius 3 that's centered at the origin. Well, that's just going to be x squared plus y squared equals 9. And if we want to find the implicit derivative, we're going to have to indicate which variable we're differentiating with respect to, which is almost always going to be x. And then we're going to have to indicate our other variable, which is going to be y. And if we press enter, we get that y prime equals negative x over y. So that's pretty useful. And suppose we wanted to find the implicit derivative at a point. So we use our vertical bar again. And then suppose we wanted to find the slope at x equals 0 and y equals 3. Well, then we just get that it's 0. And notice that we have to separate our different constraints, x equals 0, y equals 3, with an and. So that's how to integrate and differentiate numerically and symbolically